Okay, today we're going to do volumes of rotation. And for our first example, we have the shaded region right here. And if we rotate it around the x-axis, we are going to get some type of shape like this. Now you can see this shape over here. It looks like it's made out of a bunch of discs. So let me explain that a little bit. So for this example, if I take each rectangle and rotate it around the x-axis, it's going to create these discs that you see over here. So we have the first 4 discs shown, and that's if you take these 4 rectangles and rotate them around the x-axis. And if you do that for all the rectangles, then you'll end up with all these discs that you see over here on the right side. Let's look at another example. Again, if we take this shaded region right here and we rotate it around the x-axis, it's going to create this type of volume that you see over here. Now you might notice that this volume is a little bit bumpy, and that's because this volume is created with a bunch of discs. The real volume would be nice and smooth. Let's look at another example. Here's an example of a Hershey's Kiss. So the function that we're rotating might look something like this, just as an example. That could be the function. And you rotated it around the x-axis, it would create something like this. Now this is just a bunch of discs. The real one would be nice and smooth, so it would look like this Hershey's Kiss over here on the left side. Let's have a look at another example. Okay, this is a trig function. For this example, we're just looking at one of the rectangles. Remember, we usually have an infinite number of rectangles for a real volume or for a real integral. So here we're just looking at one of the rectangles, and if you took one of these rectangles and just rotated it around the x-axis, you would get this disk that you see right here. And of course, to get the volume, we use an infinite number of those rectangles, and we rotate them all around the x-axis, and that gives us our volume. Now today we are learning the disk method, so we want to start by looking at a disk. A disk is basically a circle, but it's like a prism. It's like a really thin cylinder. So it does have a width. Our width we're going to call dx, and that width is infinitely small but not 0. So it's extremely thin, extremely small, but not 0. So today what we're going to have to do is we're going to have to do the integral, and then we put the volume of one disk right there, and then we'll fill in a bunch of disks from the starting amount. We're going to put that's our lower bound, and then all the way to the ending amount. So we're going to fill in a bunch of disks. Again, the volume of one disk is going to be the area times the height. And since it's a circle, the area of a circle is just going to be pi r squared. So that's what's going to go right here. We're going to have pi r squared. And then dx is basically like the height. It's an infinitely small height, but it's not 0. Okay, for our first example, we're going to do the sine function. Now for the sine function, our shaded region is going to be shaded from 0 all the way to 2. So it's this shaded region right here. And we're going to rotate that shaded region around the x-axis. So it's going to be kind of like this. When we rotate it around the x-axis, each of those rectangles are going to create disks as they rotate around the x-axis. So it's going to be kind of like a bunch of disks. And we need to find the volume of one disk. That's what goes inside of our integral. So we know that it's going to be pi r squared, and then dx is going to be the height of each disk or the width of each disk. And you can see that we're starting from 0 and we're ending at 2. So we're going from 0 to 2. So our bounds are going to go from 0 to 2. We just need to figure out what is the radius. I need the radius as a function of x. So our r is basically this distance over here, and I'm going to find that distance by doing just top minus bottom. So the top is just the sine function, and then minus, and then the bottom is just y equals 0. So it's going to be sine of x minus 0, which is just sine of x. So I can replace my r with just sine of x. So there we go. This is going to be our r. And just as a reminder, we're filling in these disks from x equals 0 all the way to x equals 2. So it's going to be this kind of picture here. We're just going to have a bunch of disks, and this is the volume of one disk. It's going to be pi r squared times the height, and the r is sine of x minus 0, which is top minus bottom, And so that's why it's just going to be a sine of x. Let's plug this in our graphing calculator and get an answer. Okay, I want you to notice that I did the integral and then I did pi r squared, but I didn't put anything for the r. And my x is going from 0 to 2. So now I'm going to plug in my r, and my r is the sine of x function. And we'll push enter. And there we go. That's our answer. We can go up, push enter again, and then we'll get many more decimals of accuracy. All right, let's go ahead and put a box around the answer. Of course, I'm just going to truncate it. Remember, the AP test would accept 3.736. And that's because the 9 could round the 5 up to a 6 if you want to. I prefer just to ignore it, and I just list the first 3 decimals that I see. All right, let's go to the next example. All right, for this example, you can see that the equation is x equals y squared minus 4. For this example, you can see that the shaded region is just this region over here on the left side. And we're going to take that shaded region, we're going to rotate it around the y-axis this time. And when we rotate it around the y-axis, you can see what's happening is going to look something like this. We're going to get a bunch of disks. So that means that one of the disks is going to look something like this. So we're going to do our integral. And you can see that our integral is going to go from -2 all the way up to +2. So there'll be y values. So we're going to fill in a bunch of disks from -2 all the way to +2. But the volume of one disk is going to be pi r squared times the height. So I'm going to put pi r squared times the height. And the height is going to actually be a dy. If you look at the picture right here, I have a picture for the volume of one disk. So for most of these problems, the tough part is just to figure out what is the radius. Now, as we said before, the radius, we're going to have to do right minus left, and that'll help us figure out what the radius is. The right is going to be x equals 0, so that's why we put a 0 right here, and then minus, and then the left is actually the function. So the left is going to be y squared minus 4. Now, you could distribute the negative on both pieces, and that would give you 4 minus y squared, and that's your radius. So that's going to be plugged in right here for the r. Let's go ahead and plug it in. Okay, there we go. And again, this is our r. That's usually the hard part. And again, our bounds went from -2 all the way up to +2. So that's why we go from y equals -2 to y equals +2. Make sure it's a dy, and every letter should be y. So let's go ahead and plug this in our graphing calculator. All right, I want you to notice that I did the integral of pi r squared, but I haven't plugged in my r yet. And you'll also notice that my y goes from -2 to +2. So now let's go back inside and let's plug in the r. The r is going to be 4 minus y squared. 4 minus y squared, then we'll push enter. And we're getting 107.233. Of course, I want to go up, push enter, and now I can see many more decimals of accuracy. Let's go ahead and put a box around our answer. Of course, I'm just going to truncate it. So my answer will be 107.233. And that's it. Let's take a look at the next question. All right, for this example, it's kind of like rotating around the x-axis, but instead of being y equals 0, which is the x-axis, it's going to be y equals 5. So it's just going to be shifted up a little bit. Now, if you look at the radius here, it's kind of like one rectangle. And if we rotate it around the line y equals 5, it's going to create a bunch of disks that look something like this. And so that means that one disk would look something like this. So we're going to do the integral, and then we're going to put the volume of one disk in front of our integral. The volume of one disk is going to be the area of the circle, so pi r squared, and then the width is going to be dx. Now we're going to fill in all these disks starting at x equals -2, and then going all the way to x is equal to +2. So we're going to go from -2 to +2. We're just going to fill in a bunch of disks from the beginning all the way to the end. Now we get to the hard part. The hard part is figuring out what is the radius, what is the r. So this is going to be top, minus, and then bottom. You'll notice the top is the function y equals 5. So the top is going to be 5. Then we're going to do minus. And the bottom is just the function, it's just the curve. So the bottom is going to be x squared plus 1. So So you'll notice we have our x squared plus 1 right there, and that would be your radius. So that's going to go inside these parentheses here, and the only thing we're going to square is that radius. Now I want you to notice that the minus actually goes on both pieces. So really I have 5 minus x squared and then minus 1. So you can combine the 5 and the minus 1. And that'll just give you 4. So our radius is going to be 4 minus x squared. So let's go ahead and plug that in for the r. Okay, and just as a reminder, that's the r. It's 4 minus x squared. And now we're done. We can type this in a graphing calculator. This is actually the same exact integral we had on question number 2. Let's look back at question number 2. So for question 2, the only difference was that you had y. So you just had a different letter instead of x. Now we have the letter x. We're going to get the same answer. So we're going to get 107.233. So that's it. That's our final answer, 107.233. Okay, for number 4, the shaded region is going to be this region right here. And it basically stops right there at x equals 5. We are going to rotate it around this axis. So it's almost like the y-axis, right? But it's x equals 5 instead of x equals 0. So this is going to be an example that's kind of like a right minus left. You'll notice that when we take this rectangle here and rotate it around that axis, you're going to get a bunch of disks that look like this. And so if we look at just one disk, we can figure out the volume for just one disk. It's just going to be the area of a circle, so pi r squared, and then times the height. The height is dy. Of course, our y values go from -3 up to +3. And now all we need to do is just figure out what is the r, and then we'll be done. The r is always the hard part. This is going to be a right minus left example. So the right is going to be 5. Then we do minus, and the left is just the curve. So the left is going to be y squared minus 4. So there's the left, it's y squared minus 4. Now let's go ahead and simplify this radius before we plug it in. This minus goes on both pieces, so you're going to get 5 minus y squared plus 4. So 5 plus 4 gives us 9. So that's going to be your r. Your radius is going to be 9 minus y squared. Let's go ahead and plug that in for the r. And that's it. We're basically done. We can plug this in the graphing calculator. I do want to point out that this is our r right here. And so we do have pi, and then r, and then squared. So that's the area of the circle. And the circle is the base of the disk. And then we have dy, which is the height of the disk. Let's plug that in a graphing calculator and see what we get. Okay, there we go. We're getting 1296 over 5 pi. Or as a decimal, we're getting 814.301. Of course, I usually like to see more decimals of accuracy, so I'm going to go up. I'm going to push enter so I can get a little bit more decimals of accuracy. Put a box around the answer. I kind of like this answer better because it's an exact value. If I had to give a decimal answer, I would just truncate this, and I'd give 814.300. If you do truncate your answer, make sure you put both of these zeros. Those zeros are very important because what it means is that that's not an exact value. It's either a rounded number or it's a truncated number. Of course, the best answer would be the exact value. So 1296 over 5 times pi would be the best answer for this question. Okay, for this example, they're just giving you 4 points, and they're telling us that that's a trapezoid. And we want to rotate that region, that shaded region, around the x-axis. The tricky part for this example is just to notice that the top of that would just be a line. Now that's going to be important later because to find r, we've got to find the distance from here to here. So we need top minus bottom. And the top is just going to be the equation of that line. Now I want you to notice if I take each rectangle and rotate it around the x-axis, I'm going to get a bunch of disks that look something like this. So again, just one disk would be something like this. And that'll help me because I'm going to do the integral. And the volume of one disk is just going to be pi r squared. You'll notice that the width or the height of each disk is just going to be dx. And of course, my x is going to go from 3 all the way to 6. So I'm going to fill in those disks from 3 all the way to 6. And the hard part is always finding the r. What is the r? Now it's pretty obvious that the bottom is going to be 0, but what is the top? What's the equation of that line? Now the equation of that line is going to be y equals mx plus b. The b is the y-intercept, and you can see that it's 2. And we got to count the slope. You can see I'm going up 2 and right 3, so that's going to be 2/3 for the slope. So again, if this is the radius over here, this blue rectangle, and the radius is going to be the top minus the bottom, and that's just going to be the line 2/3 x plus 2 minus, and then the bottom is just y equals 0, so it's just minus 0. And that'll be your radius. So it turns out our radius is just going to be 2/3 x plus 2. Let's go ahead and plug that in right here, the 2/3 x plus 2. Plug it in for the r. There we go, that's the r, it's 2/3 x plus 2, and that was actually the hard part of the problem. We can go ahead and plug this in our graphing calculator and get our answer now. Again, just as a reminder, I'm doing the integral of pi r squared, but my r is just a parentheses. And my bounds, it says x goes from 3 to 6. So the last thing I always plug in is the radius. In this case, our radius is 2/3 x plus 2. Let's plug that in. Then we'll push enter. And we're getting 76 pi for our answer. And if I wanted a decimal answer, I can push green enter. And it looks like that would give me 238.761. If I want to check more decimals, I go up, push enter, and you can see it's 0.7610, so that looks fine. Put a box around our final answer. And I always prefer the exact value, so I'm just going to go with 76 pi as my final answer. Okay, for number 6, we have an ellipse that's rotated around the x-axis. You'll notice that all we need is really just the top. We can rotate the top around the x-axis, and that'll give you the same thing as if you rotated the entire ellipse around the x-axis. This one's kind of like a football. I always like to start with one of these little rectangles, and if you rotate it around the x-axis, you would get a bunch of discs that would look something like this. And again, that means that one of the discs would look something like this. So for our integral, we can just do pi r squared and then dx for the width. And so this would be the volume of one disk. But we're going to fill in a bunch of these disks, and we're going to go from -3 all the way to +3. So my bounds go from -3 to +3. And the hardest part is always finding the r. What is the r? And if this blue rectangle over here was my r, then I would just need to do the top minus the bottom. The top is just the function. So for an ellipse, if you solve it for y, you're going to get plus or minus, and the plus is going to be the top. So again, we're doing top minus bottom, and the top is going to be this right here, and then minus, and then the bottom is just the x-axis, so that's y equals 0. You don't really have to put the minus 0. So that's going to be your radius. We can go ahead and plug that in right here for the r. Okay, there we go, and that's our integral. Again, this is our r. That's always the hardest part. But again, you notice we have just pi, and then r, and then squared. That's the area of the circle. And then the height of the disk is just going to be dx. You'll notice we're going from x equals -3 to x equals +3. So we can plug this in our graphing calculator and get our answer. All right, looks like we're getting 16 pi for our final answer. Let's put a box around it. And just as a reminder, if you don't know how to graph an ellipse, you want to divide everything by 36 so that it's equal to 1. And then you want to write the bottom as something squared. So you see we have a 3 squared, and it's below the x. So that means you go 3 in the x direction. So we're going to go 3 to the right in the x direction and 3 to the left in the x direction. And then on the bottom of the y, we have a 2 squared. So we're going to go 2 in the y direction. So that means we're going to go up 2, and then we're also going to go down 2 from the origin. And so that's a reminder of how you would graph the ellipse. All right, we're doing our very last example. We're going to take the region bounded by these curves. We're going to rotate it around the y-axis. So we're taking this region right here, and we're going to rotate it around the y-axis. So we'll have a bunch of disks that look like this. And again, that means one of the disks looks like this. We can do our integral. Our integral is going to be pi r squared, and then our width is dy. And our y values go from 1 all the way to 3. So for our bounds, we can go from 1 to 3. And now we just need to figure out the r. That's always the hardest part. So if this was our r over here, we would need to do the right minus the left. The problem is that our function is solved for y equals. So we need to solve it so that it says x equals. So we're going to take this function y equals e to the x. We'll do ln of both sides. Of course, ln of e cancels, and then we'll be able to solve for x. We'll get that x is equal to ln of y. So the right one is going to be x equals ln of y. Of course, the left is just x equals 0, so it's just 0. So just as a reminder, in order to do the right minus the left, you have to solve everything for x equals. So this one was a little tough because we started with y equals. So we had to solve it for x equals so that we had a function of y. Now we're done. We have our r. The r is just going to be ln of y. So we can go ahead and plug it in for the r. Okay, after plugging in the r, we're going to get this integral right here. Let's plug it in our graphing calculator and see what we get. Okay, there we go. Our answer is going to be 3.233. Let's go ahead and truncate that, put a box around the final answer, and that's it.